Good morning. I'll be presenting my project titled Video Processing Applications and Content-Based Retrieval. What is video processing? Video processing serves as a means of extracting relevant information from video content. Instead of relying solely on manual methods, video processing automates the analysis and interpretation of visual data. Video processing employs statistical methods to make sense of the complex visual information. Various techniques are employed in video processing to enhance and manipulate the visual data, such as filtering, segmentation, and feature extraction. Historically, the process of data extraction from videos relied on manual tagging and labeling. These traditional methods are not only time-consuming, but are also susceptible to human errors. As the volume of available data increases, the limitations of manual methods become more pronounced, leading to issues regarding the scalability and effectiveness of content retrieval systems. Why cricket? The rising demand of sporting analytics, the increasing popularity, and the wealth of data available makes cricket the ideal choice for this application. This is an overview of the various pre/post processes that we look at in this paper. There is converting to grayscale, similarity measurement, thresholding, blurring, and optical character recognition. Converting from RGB to grayscale is necessary because it simplifies the image data, enhances computational efficiency, and allows for feature extraction. The important element of content-based video retrieval is the distance metric, also known as a similarity measure. The Euclidean distance between the database and the query are computed and used for ranking in traditional retrieval. If the gap is lower, the query frame resembles the database frame more. The table shown highlights the most popular distance measurement methods. By performing similarity analysis between nearby frames, we can determine if they should be considered for analysis. In local thresholding, the windows or subpictures are employed instead of the complete image, since the smaller sections may have more uniform features. This process is crucial as it allows for the isolation of the foreground text from the background, allowing for uniformity and ease of processing. Blurring is typically used to remove noise from an image. The weighted averaging filter is used to blur image by calculating the mean of a pixel's neighbors. The type of mean utilized is determined by the filter. Gaussian blurring is performed by applying a low-pass filter to the image, which smooths it and removes noise and small details. This contributes to a more even gradient of pixels for the edge detector to work with. Preprocessing is a crucial step that must be taken before OCR can be used. TestRack OCR was used due to its ability to effectively extract text from an image. Text localization can be used to reduce the area in which preprocessing can be done. We can utilize bounding boxes to isolate the critical text data from the rest of the image. Thresholding can then be used to create a binary image by separating the text from the background. This further simplifies the image by enhancing the contrast between the areas with and without text. Noise removal and image denoising techniques can also be considered if the image is particularly noisy. Optionally, image rescaling can be considered as well as contrast enhancements. The architecture can be seen to the right. Firstly, an input image containing text is fed into the TestRack OCR process. Thresholding is used to convert the image into a binary format. By improving the contrast between the text and the backdrop, the binary image makes it easier to recognize the characters. TestRack uses binarization to identify and extract individual character outlines, which serve as the foundation for additional analysis. TestRack's recognition algorithms are then used to determine the character outlines using statistical and pattern matching techniques. Using its training data and language models, the engine groups individual characters into words and calculates the likelihood of specific sequences. The result is the identified text that is extracted from the input image. Now we move on to the methodology. We must first divide the broadcast video into segments. This stage is necessary to perform pre-processing and allows us to isolate relevant content. The proposed method samples the input video every second and output an image. These images are named incrementally and stored in a separate folder for pre-processing. The OpenCV library within Python will be utilized for this task. The input video is an ODI broadcast consisting of over 8 hours of video data. Therefore, we obtained a total of 29,033 images, some of which can be seen here. Here we can see the original image going through the stages of pre-processing mentioned previously. By creating a simple loop within Python, we can incrementally perform pre-processing and OCR, respectively, on every extracted image. Steps were taken to reduce the workload by designing a text recognition system within Python to ensure that pre-processing and OCR were only applied to frames that contained text-based data. We obtained an accuracy of over 90% for every frame that was inputted into the system. The primary errors arose from misreading some values and incorrectly assuming that the text was present in some images. The data obtained was stored in a .csv file containing the frame name, number of runs, and number of wickets. This stage attempts to correct similar errors by applying thresholds to ensure that all outliers are removed. We can now observe the result of cleaning the raw data. Exploring dynamic threshold strategies that adapt to varying lighting conditions or text contrasts may improve the robustness of the pre-processing stage. Further exploration into real-time processing and streaming methodologies would extend the applicability of the proposed method to dynamic and evolving content scenarios. Additionally, mechanisms for user feedback can be incorporated to facilitate continuous improvement through user corrections and validation of extracted information. The proposed methodology provides a systematic approach for extracting insights from cricket broadcasts, facilitating in-depth analysis of players' performance, team dynamics, and match strategies. Additionally, the text-based image retrieval, or TVIR, techniques prove useful in content archiving and retrieval, allowing for efficient access to specific moments and statistical highlights for historical analysis. Integration into the broadcast production workflows enhances live broadcasts with real-time data extraction, offering broadcasters innovative tools for dynamic content presentation. Beyond sports, the adaptability of TVIR can be applied to media monitoring, event documentation, and automated information extraction. In conclusion, this research endeavors to revolutionize the landscape of video processing and content-based retrieval with a specific focus on cricket broadcasts. By proposing a text-based image retrieval methodology, we address the limitations of manual tagging and labeling and highlight the need for efficient and accurate content extraction. The exploration of advanced optical character recognition techniques and dynamic thresholding strategies allow for improvements in character recognition accuracy and pre-processing robustness. We also highlighted the importance of data cleaning in the removal of outliers. The proposed research holds potential not only within the domain of sports analytics, but also across several applications such as content archiving, broadcast production enhancements, and educational platforms.